Welcome to this explainer. Today, we're going to completely transform how you think about machine learning. We are taking it right out of those isolated lab experiments and turning it into an automated, highly scalable, cloud-based production powerhouse. So, whether you're an aspiring data scientist, a software engineer, or maybe a CS student desperately cramming for finals right now, you are in the right place. This is your complete masterclass on MLOps.
You know, it's arguably the biggest question for engineers and students alike. What actually happens when your model leaves the safety of the lab? Why do so many brilliant machine learning models, stuff that hits incredible accuracy on your local laptop, never actually survive to see production? Well, the reality is pretty harsh. Without automated systems, manual deployment processes just completely break down out there in the real world.
To answer that, and honestly, to solve this deployment crisis, let's take a quick look at our roadmap for today. We'll start with the core concepts in the paradigm shift, then explore the major platforms in the cloud titans, head down into the engine room of pipelines, check out the front lines of monitoring, and finally, wrap the whole thing up with a rapid-fire exam sheet perfectly tailored for your university assessments.
All right, let's jump straight into Section 1, the paradigm shift.
Here is the crucial takeaway. MLOps, or machine learning operations, isn't just a single tool. It's not just one specific piece of software you install. It's actually a really powerful formula. It seamlessly combines machine learning, DevOps, and data engineering to totally automate the entire model lifecycle. It is literally the essential bridge between just building a cool model and actually making it useful at a massive scale.
To put that into perspective, think of traditional ML as slow, manual artisan craftsmanship. You're dealing with manual deployments, you've got barely any monitoring, and updates are just painfully slow. MLOps, on the other hand, is your highly scalable automated factory line. It gives you continuous monitoring, full version control, and lightning-fast updates straight to your production environments. Night and day, right?
So let's see how this builds into an actual workflow. This automated factory floor follows a really strict life cycle. It moves step by step, starting with data collection and preparation, flowing right into model training and evaluation. And hey, if the model is actually good, it gets pushed into a model registry, which you can think of as essentially version control for your models, before finally heading out to deployment, monitoring, and eventually automated retraining.
Okay, moving right along to Section 2, the cloud titans.
Now, if you are currently taking notes for your 5-mark exam questions, you'll definitely want to pay close attention to architectures like AWS SageMaker. This is Amazon's fully managed ML service. Notice the logical flow it follows. We pull our raw data from S3 storage, we move it into a SageMaker notebook for development, push it over to model training, log that artifact in the model registry, and then finally deploy it as an active prediction endpoint.
But AWS definitely isn't the only player in town. Microsoft's Azure ML Studio features an absolutely incredible drag-and-drop designer interface and automated model building, which then deploys via REST APIs. And then over in Google's ecosystem, Vertex AI really stands out with its dedicated feature store, perfect for managing reusable input features. Plus, it's got built-in model drift detection. Pretty neat.
This perfectly sets up a classic 7-mark comparison question for your exams. The key differences really come down to deployment and pricing. While Azure leans heavily into a subscription-based model utilizing REST API deployment, both AWS SageMaker and Google Vertex AI operate on a more pay-as-you-use structure, and they're heavily focused on deploying to direct endpoints. Definitely memorize those distinctions.
Let's dive a little deeper now with Section 3, the engine room.
Right at the beating heart of this engine room is the CI/CD pipeline. That's continuous integration and continuous delivery. It automates literally everything. The second a developer makes a commit into source control, boom, the system triggers a build pipeline. That immediately kicks off automated model training, rigorously tests the resulting model, and then relentlessly pushes it out to deployment and monitoring. Zero human intervention required. Honestly, it's the dream. Let's break that down just a tiny bit further. Notice how continuous integration, the CI part, handles all the validation. It's checking your code, running unit tests, validating your dataset, and actually building the model itself. Once all of that passes, it hands the baton over to continuous delivery, the CD part. That takes care of packaging the model artifact and pushing it live to an endpoint so your users can actually interact with it.
Of course, none of this automated magic works without data. And machine learning requires massive, sometimes frankly absurd, datasets.
That makes scalable, highly available cloud storage an absolute prerequisite for any MLOps pipeline. So whether you're using Amazon S3, Azure Blob Storage, or Google Cloud Storage, these services provide that crucial, bulletproof reliability you need to feed your continuous training pipelines.
All right, moving out of the engine room and into Section 4, the front lines.
So how do these models actually interact with the real world? Well, they're typically delivered via REST APIs. An application programming interface basically acts as a messenger, enabling a client application to seamlessly talk to your ML model. For example, a loan application on a smartphone can send JSON inputs, like someone's age and income, through the REST API, and instantly receive back an automated prediction of approved or denied.
But as we all know, real-world data changes constantly. And this brings us to a major exam topic that trips up a lot of students. You've got to understand the difference here. Data drift happens to your inputs before the prediction even occurs. The actual real-world data distribution shifts. Model drift, however, is the degradation of your model's accuracy after it's been deployed. Basically, the world changed and your model just became outdated.
Finally, let's wrap this up with Section 5, the exam cheat sheet. We've covered the entire MLOps workflow, so let's lock in this knowledge with a rapid-fire exam strategy. For those quick 2-mark questions, focus strictly on core definitions. Don't overcomplicate it. Memorize that MLOps formula we discussed. Be able to accurately define an endpoint as a deployed prediction service. Clearly separate model drift from data drift. And just be ready to rattle off those 3 major cloud storage services.
Now, when it comes to the 5-mark questions, examiners want to see that you actually understand how these pieces connect. You must be able to clearly explain architectures step by step. So be ready to write out that SageMaker workflow, flowing all the way from S3 to an endpoint. Be ready to summarize the key features of Azure ML or list out the exact pipeline stages for CI/CD that we looked at back in the engine room.
And for those big, heavy 7-mark questions, they want comprehensive workflows. You should be fully prepared to actually draw the entire CI/CD block diagram on paper. You might need to write out that complete cloud platform comparison table comparing AWS, Azure, and Google. And you'll definitely need to articulate the distinct advantages of continuous monitoring in a production setting.
What we've got here simply breaks down your examiner's grading rubric. Honestly, this is how you win. Structure your answers efficiently, based exactly on what they are looking for. Give them quick facts for 2 marks, structured components for 5 marks, and deeply integrated, fully illustrated systems for those 7-mark hitters. Give them exactly what they want.
So, as we wrap up this explainer on how MLOps turns artisanal, manual experiments into highly scalable, reliable factories, I want to leave you with one final thought to ponder. As these continuous integration and continuous delivery pipelines become fully automated and increasingly intelligent, will the engineers who build the factories eventually replace the scientists who design the models? Think about it. Keep learning, and I'll catch you in the next explainer.